So today's talk is about networks. Yeah, that very much fits within your graph network. But it's a network of the multiple systems that are interacting, and I'm really looking at large networks. Now I'll give you a few examples. So most of the material is kind of a general overview. I'm not going to the difficult mathematical stuff that we can all read in the book. And it really exists. It's not a glitch, but it really exists in the book. It came out last year from Cambridge University Press. And you're more than welcome to dig into the information. I see how it works. Yeah. You know?
Yeah, it.
Yeah. So this book basically consists of 3 parts. And I will kind of delve superficially on the first 2 parts. So this is the book. It's about data-driven, starting from data, and in an approach which I developed also previously. It's a kind of better data speak for each other. How much more information you can get out of the data, which I think for large-scale networks adds an additional grand challenge. I actually will see there. So that's a data-driven perspective. And here are some of the people who really contributed to that change with you. He's in China now, professor. With whom I cannot work together anymore because of some strange political reason. It's fascinating. I worked with him about 10 years or so. But very, I would say, very, in a very prosperous manner. And then suddenly there come some politicians working together. Very extreme. Anyhow, and that is what the BC is doing. So these are the 3 parts. In identification, the general policy in identification is that you have to somehow parameterize it, somehow give it hands and feet from a mathematical perspective. And in large-scale systems, this is really adding on an additional challenge. And of course, once you have parameterized it, it has little kind of based on as little prior knowledge as possible. Then, of course, you have to identify it. And the first step is to validate and apply it. And that's also what we do. And we don't only theoretical people, we try to see things working, after all, I'm also an engineer. I said I will only develop all these elements, the first 2 parts, from a very superficial level. You whet your appetite, basically, and read more into the book. So let's first look into the parameterization. But also before that, give some examples. You guys know much more. I also heard water networks, all kind of networks that are here, or of interest here. But the things that we looked into was large-scale adaptive optic systems. Now, these are systems by which people try to find out extraterrestrial life. They're somewhere in the universe, some other specimens are watching us. Which I think, as a Christian, I believe it is true, but that's a different story. Now, these are kind of ground-based telescopes, and to increase the resolutions of these telescopes, you have to make them bigger and bigger. So right now, the European and Americans, they are competing with one another, and this is a sketch of the extreme large European telescope, which will be operated in Chile, and it's like half a soccer field. That's what this telescope is about. It's very ambitious. And of course, you can't build that anymore in one structure. And that's why this primary mirror is consisting of, say, about 1,000 individual elements, 1,000 dynamical systems that have to operate with respect to one another to the nanoscale. That is very important for having accurate images. Now, this primary mirror on itself is useless, because you have to look towards the atmosphere, and that's kind of pictured here. That's the kind of picture by the atmosphere, which most of the universe, where the light is progressing through million years of light years, is kind of very nice. And there is no aberration caused to the light. But only this very last point, 100 kilometers in the stratosphere, there's a lot of turbulence. And what then happens with the light beam is that diffraction. It's kind of scattering of the light taking place. And even if you have this very large mirror, say half a soccer field, When you don't do anything about that, you have the same resolution as Newton's telescope, which was about 3 centimeters or 10 centimeters large. So you have to do something special about that, and that's where control comes in. But the most important part to do control is to get insight about these aberrations, because these fluctuations is very difficult to model that. There are some sensors that you can use, but this is a temporal phenomenon and a spatial phenomenon. Over the whole field of view of this telescope, this turbulence is changing, that's a spatial component, and it is also changing in time. So spatial temporal dynamics need to be modeled very accurately, and it's a large-scale system. So the device that is being developed to control or to compensate for these aberrations are adaptive mirrors. Now this is about the 3-meter adaptive mirror with about 10,000 activators. And each of these activators, each of these small elements, well, in this kind is a kind of membrane mirror where you have behind the activators. When one activator is pushing the membrane, it's influencing its neighbor. So there's interaction between these dynamical systems. And that's where things become interesting. So there is the dynamics in the activator, but also in the distribution, in the disturbance. There are dynamics over the large-scale system. Because you have to look from the sensor side to measure these aberrations. By the way, you cannot measure directly, but that's another issue. You have to think about the multiple of this number of activators. So when you have a system, say with about 10,000 activators, your sensor side is about 20,000 or even 100,000 sensors. So you easily talk into dynamical systems with 10 to the 4, 10 to the 5, 10 to the 6 activators and sensors that you have to do. So doing that in a centralized manner is out of the question, even with our powerful computers, because these devices have to be controlled with a frequency of 2 kilohertz. And that's what you have to think about, right? That was quite a challenge, a motivating challenge for us to develop new type of methodologies. And then many more examples: active boundary control, formation flying, cellular dynamics, water networks, and many more things. So let's look into the first part of the book of our research agenda. And you know how this research agenda developed. You write a proposal, and then after the research is done, you do reverse engineering, and then you start to split up everything in very nice parts, which was not there in the beginning, of course. There in the beginning, we tried to look at identification, and then we found out that parameterization is kind of an actual very important problem. So how do you parameterize these large-scale systems? There are many ways of parameterizing or modeling dynamical system, transfer functions, state-based models, and many more of these devices, hybrid systems, blah, blah, blah. But let's look at the transfer function models, where graphs come into as kind of naturally. That's what I will start off with graph function, graphs to define these structures of these models. But more importantly, I look into a new class of models that I have introduced to you, which I indicated with bar clause, as a way to preserve this data, let the data speak for itself. It's a kind of a black box structure. While in this graph, you have a kind of a priori specified topology, which in the data let the data speak for itself, I presume not to be available. And that's where these more black box models come into the picture. As an illustration, I will start with one, but then maybe focus on the Kronecker-based models, opening up the avenue for tensor-based models. In general, an input-output model where the output is Y and the input is U, and the perturbation is kind of a filtered white noise. You have P outputs and inputs, and then you see already the challenge here. When P and M, or say 10 to the 4th, 10 to the 5th, have an extreme large number of transfer function models. If you presume no structure, if you don't apply on the structure in these transfer function matrices G and H. So that's what I call the additional structure for large-scale systems, is how to parameterize these transfer functions in a systematic manner. Of course, if people don't know, and that's what we did also in the system identification area, if we have a challenge there, we'd like to rely on a priori information. That's what I have since the development of such things, tried to come up with a completely different approach, get as much information out of the data as possible. But you see immediately, if you have 10 to the 4, you have 10 to the 8 transfer function that we have to parameterize. And then we have a zillion number of parameters how to do it. Luckily enough, there should be structure in that large-scale system, but how to find that from the data? And as said, if you can't find it from the data, you have to a priori specify it yourself. Let's look at this graph for a minute. You have your the nodes here, or your measured data. You have your measured outputs, your measured inputs, and then you presume you a priori specify a certain topology, and that there is some interaction between these inputs and outputs, and there also might be influences between the different outputs themselves. This a priori. And finding that kind of network structure from the data, it's an issue. People have looked into that, but also the identifiability. Once you have parameterized these transfer functions, can you find the parameters from the data? And that's also an interesting question, which is the identifiability question. It's kind of also treated in my book, but I don't want to go into details because I want to find from the data whether there is a connection between wire 3 and wire 4 or not, and let the data specify that for itself. These are sparse kind of representations, and you can extend that to more generic black box models, so to say. And we start off with a simple vector autoregressive model, which you all know, I presume. It's a kind of starting working horse for many more generic models, argmax and box shapings, etc. It's really the starting. And it's a very simple example. It's a tool like AR model. And then you see the challenges. There are some temporal dynamics that you have to specify, and which is kind of indicated by the time indicator, that's K, generally used in my notation. But there's also the spatial structure that you have to define, and that's the structure in the coefficient matrices of your dynamic model. So that's the additional parameter that you have to specify. And that's where graph comes into the picture. Granular causality graphs, they try to specify both the relationship in the dynamics of the Y signal here, in the input, but it's very simple, just the Y. And they also try to specify the structure into the noise. So the noise I assumed to be temporally wide, that's a temporal part, but to be spatially correlated. That is indicated by the fact that it's zero mean and it has a certain covariance matrix sigma e. Now, generally, what we observe in practice is that the inverse of this covariance matrix has a sparse structure. That the inverse of that matrix is highly sparse. In many of the applications we have been looking at, not the covariance matrix itself, but its inverse. And to kind of parameterize that sparse structure in that inverse covariance matrix and in the coefficient matrix AI, this granular causality graph can be used. It consists of nodes, V of your graph, and edges in the deterministic part, which I call also the A coefficients, and the stochastic part, which is the covariance matrix. And then you know that this graph has certain connections when there are non-zero elements. But that's something you have to specify a priori or try to find that from the data, and which is quite a challenge. Yeah? And to really find that graph structure from the data with this type of models. Also, that immediately indicates that you have to look into not anymore simple squares, but you have to put in constraints, like L1 constraints, to somehow try to find the sports that you need there. But this is quite a challenge there, how to deal with that sports field that covariance made it inverse. And that's where we have come up with a generalization of this Verhaegen model, which I call the generalized Verhaegen structure. And that's based on the fact that this covariance matrix of the signal E here, it might be dense, but it's in versus sport. Then, of course, because it's a positive definite matrix, which we assume, it has a kind of spectrum, how to say that, a square root, and it has a square root. And if the square root is invertible, if you pull that out of the covariance matrix and put that in front of this equation, you get a generalized Vark structure. But the generalized Vark structure, where this matrix here now is that square root of that covariance matrix, it can be presumed to be a lower triangular matrix with units on the diagonal, where now the elements of your disturbance has a diagonal covariance matrix, so both that has now become temporally wide and spatially wide. And then by this parameterization, you have this benefit. Now, what is the extreme benefit of this model structure? Is that you have to impose any generality here, that's the first important thing, and that you can do the system identification in a parallel manner. And because you can pull out row by row of this equation independently, because the fact that the noise is uncorrelated from each other. So this is already a way that parameterization helps you to solve or make the identification problem tractable. The very important is these elements, just an illustration. And you don't lose anything. And also, if you have found this matrix, you can reconstruct the covariance matrix if necessary. But everything is now sparse, and because you can do it in a distributed fashion, all the rows independently, you can easily impose kind of sparsity in this coefficient matrix by L1 constraint. So that is L1 constraint in general of very small scale least squares problems, so that you can solve. We have applied it also to our astronomy example with lots of success. And you see here, this is just, I would say, and that's also the philosophy of the book, I've created many kind of openings towards innovative research that can build on this. And one of the things you can easily do, and from the Vark, you can introduce the input signal that your Vark's models. You can have more generic models about the noise, then you have Armax models, etc., which we haven't done yet, but I think there's lots of room for innovative research here.
Sorry. So just to understand the step, so you made the change on the covariance matrix of the noise, no? Right?
Well, I didn't make a change, I just made the assumption that the noise here is completely dense and positive definite, and hence it has a square root.
Yeah.
And the square root is kind of just parameterized in the next model as an additional term in front of the measurement.
Okay, so this is equivalent to the first.
Absolutely, completely equivalent. But with the advantage now that we have kind of disconnected each of these things, it now has become not only temporally wide, but also spatially wide. And that allows distributed calculations, which you couldn't do with the other one because all the noises are coupled.
But so the covariance of the Y, for instance, now is the same as the covariance of before.
Absolutely. Yeah.
Even if there is this A matrix there.
Absolutely. Yeah. The same outputs in the same quantity that you mentioned. It's another way of parameterizing which has this interesting properties.
But the A1 and A2 might have lost their structure now, right? Their sparse structure. Because
you see that is a very good point. If A1 and A2 are sparse, because the square root of this, because the inverse covariance is also sparse, the multiplication of two sparse will be constant. And that's what we have seen in the application. That's where we really arrive. That's a very good point. You might lose some of the sparsity. And because when you multiply two sparse matrices, the length of the sparsity might change. But indeed, of course, there's a price to pay. It's much more interesting than before. Okay, so this was an example. I'm just giving some examples of a sparse parameterization, where you try to limit the number of non-zero elements that you want to find. But there is another way that we look at it. It's allowing the parameters to be dense, the data sparse. And so these matrices might be completely filled but highly structured. And there are many examples in linear algebra, for example, a tuplet string. You know, Tucker's matrix or Verhaegen matrix are typical examples of that. These matrices are completely dense, but they are parameterized by just only the top row, last column, or something like that. So this is the idea there, and there are many generalizations of that, like same separability and many more of these elements. So this is now the next illustration I want to give of these input-output models. And for that I introduce very simple, it's a kind of preliminary towards tensor calculus, and this is a sum of chromatic product matrices. And that's where we parameterize large-scale matrices in terms of the multiplication of their factor matrices. And in terms of factor matrices, and these factor matrices are multiplied by chromatic products. And you know, chromatic products have the tendency to blow up dimensions. And so the first matrices are of these small dimensions, M1 and M2, etc. The chromatic product is multiplication of these dimensions. So with these type of things allow us to parameterize dense large-scale matrices with small-scale factor matrices. So that was the idea. And tensor calculus is an advanced way of doing that. So now the issue of to use that machinery, where we have used that, of course, that is our matrix, the number of chromatic products that we have in here is the chromatic rank. And there's a definition, and in such a matrix as chromatic rank R. When you vectorize each of these individual matrices, put them next to one another, they should be full rank. That's a technical definition. But it's an important element to try to find out also from the data. But the advantage is that when you have to do operation on these matrices, parameterize of sum of chromatics, you have an order of magnitude gain in all the calculations that you do, even more than that. And so if you have to multiply in such a matrix with a vector, it is an order of magnitude faster, and n is the large dimension, 10 to the 4, 10 to the 50 of the thing, and you gain at least. If you do product of matrices, it's an enormous reduction of calculus there. Inverse is a more difficult one. You don't, it's not a kind of closed algebra, so to say, and the inverse only exists or is in the same set if you have chromatic rank on matrices. So that was an issue in here. That's a price you have to pay. But if you use this class, for example, to parameterize now the coefficients of your AR model, right? You have dense matrices, you have dense coefficients. So if you do this product explicitly, which you never have to do, this becomes a complete dense matrix, but it's data source, it's parameterized by only a small number of parameters. That's what makes it very interesting. And then you can by the simple rule translate this into a bilinear model, and that's where you see the price you have to pay for a reducing number of parameters. So now you have, and before we had large-scale coefficients that could be obtained with just least squares. Now you have a bilinear problem that makes your identification problem more complex, and that's always a trade-off. And you can kind of reduce the number of parameters, putting the burden on your identification problem to become more challenging. Having alternating these squares is that, and you can also do that with global convergence results, etc. So this is the course model for just a simple AR case, and then you see the generalization to the Armax case, etc. It's just waiting to be explored.
Well, with your what you reshape here, like the vector x y k minus I, like you reshape into a matrix.
Okay, that's true. That's what you do here.
So,
So this is the vectorized case. If you go back, this is the matrix case. So if you kind of matricize this vector, these are matrices now.
yeah, but based on how or which dimension, like because
That depends on the dimensions. That's a very good question. That's a structure element on the dimension of your factor matrices. And the dimension of the factor matrices will determine how these matrices are constructed. And that's where we kind of use prior knowledge of our kind of sensor network. And the sensor network somehow determines how you determine your data, because let's look at the examples that I showed. These are two-dimensional networks. And now, of course, what people do, they collect these network data into a vector and a vectorize it. What we do, we avoid that. We just collect the data as it is physically in time, because it's a two-dimensional network. And that two-dimensional network kind of automatically gives rise to this structure of the data. So that's the real application. This is a kind of, well, to put everything in our traditional thinking, but that kind of complicates things. This is directly retrieved from the physical network. That's an advantage also. Okay, but this was just an example. Then there is this generalization to tensor calculus, which is this Verhaegen, which is also in the book, and I've been on instantly. So this is the first setup with transfer function models, and we put, of course, if those who know my research agenda in the past, we also looked at, of course, into state-space models. Again, here, simple things first, and we looked into the output error type of models, where we have your measurable input u again here, measurable output y, they might be very large, and then you really see the problem that the system, the coefficient matrix ABC are extremely large in that perspective. If you look at flow parameterization of which are the question, I think for applications we look at. And one of the, did I put this out? Sorry about that. And one of the interesting things is in the stochastic case, where you only have an output, like in turbulence fields that we were looking at, and the output is, and the input is like the white noise, which you don't know, and that's another element you can comment directly from data. But I don't go from here. This is just a working example to show all the difficulties of dealing with that. Parameterization here, in a central way, it's out of the question, as I said. But in addition now of the temporal dynamics, which is the determination of the size of the state of the system, and that's one of the challenges in the little data speak for itself approach. The spatial structure is kind of the topology of your network, topology of your dynamical network, is kind of giving rise to a special structure of the system matrix A, B, and C. And that's where the topology comes into the picture, and I will illustrate that with a working example in a minute. So that's the additional element. So additionally, if you would like to find and measure input and output data, find the structure of such a model. It's not only find the temporal structure, which is the dimension of the state, it's also kind of the pattern, the non-zero pattern in the system matrix A, B, and C. And that's a much harder problem. It's something we have worked, I think, for 5 or 6 years in order to handle a number of these issues. Again, from a data-driven perspective. If you know your topology, if you know your network structure, it's a different story. You can somehow build in a priori knowledge and kind of enforce a priori a certain structure in the system, which I try to avoid as much as possible. And there are many different ways you can a priori specify the structure. This is a very interesting framework. That's where the system matrix or a special class of this collateral product matrices. It's decomposable systems. It's a very fascinating structure by which you can, for example, model formation flying, satellite formations, etc., very accurately. And the interesting thing there, even if your system is very large scale, with a very analytical transformation and Fourier type of transformation, you can diagonalize that. So that's analytically, you can diagonalize your structure, bring it down to a very small system for which you can do whatever you like, design your filter, design your controller on a very small scale. And the inverse transformation is just plugging up that small control design or observer design to the whole system. It's a very powerful thing there. The decomposable system. It's also where we have a few generalizations there. It's really a fascinating thing. Of course, you can do that for any network. The network has to have a certain kind of repeatability structure. And that's often the case, like information flying. This is a formation of all kinds of identical systems that are kind of connected or working in a certain topology, which is also fixed a priori. And where there's one leader and others or followers, and many of these systems fit into this framework of decomposable systems. might be good to look into whether a lot of networks can also be in there. It's very powerful. I will not delve further into that, but more focus on the working parts that we have defined, from which many of the other identification problems could be derived. And that was the parameterization of block triangular system matrices. And I well into that very quickly. Now, these are the sparse parameterizations, as you will see. But then you can also have the same thing where you have full parameterization or full matrices, but that are data sparse. The same is sequential acceptability, is just an example of that. Multi-dimensional state space model, tensor calculus, etc. Just the beginning of a whole new world. So this is a three-diagonal state space representation, just represented here for the A matrix, where the A matrix is a block triangular matrix. And what it means actually is that that's a picture of a one-dimensional structure, where you have, say, a large array of dynamical systems connected in a network, and they are exchanging their state with their neighbors. And that is what's happening. Now that's important there, that you don't have access to that state information. You don't know the size of the state. And you only know that there's interaction between this. But if you model these systems into a global, so if you lift these systems again, and they all have a kind of LTI, small scale state space model, if you lift them again, you arrive into this large scale system representation where the system matrix has this block there in the structure. Now this was really the working parts from which we derived many of the other algorithms for these product models, the decomposable systems, the semi-separability, etc., from solutions to this stuff. So I would like to take the time for the second part. Oh yeah, these are the equations. Where you see now the problem here, what the problem is. So if you are interested in, say, the system in the middle, think about sigma I, system in the middle. Then, of course, you see the linearity is one thing. You don't know the size of the state dimensions. That's a challenge there. So you don't know the size of the system matrices. But you only know the input and the output of these local systems. But they are kind of unknown inputs to the system. And that's a very challenging. It's a kind of blind identification problem. You'd like to have input-output data, but there are some unknown inputs that are really influencing the system, which you don't know. This makes it very hard to identify the system. And people have tried many other things and will come up with a solution in a minute. That's the heart of this thing. Because what you want to do, well, let me not go further. And that is the challenge there. So these are the boundary systems. It is one dimension. That's just an example. We can extend this to 2D, but in the 1D case, these are the boundaries. Where you have only, say, one unknown state as an input, and these are our systems in the middle. And there are a large number of these, and there are n local systems, and local systems where n is very large, and it's 10 to 50 to 60, etc. So identifying this in a global scenario, even if it is linear, and that's something I was seducing, trying to identify in a global setting, it's out of the question for two reasons. Right? First is the dimensionality of the matrix is huge. And you know that the complexity is n to n cube, out of the question. But if you identify the global system, say the subspace, you lose the structure because you find only the state up to similarity approximation. So the structure of the system matrices, if you do it globally, is completely destroyed. And then you have to impose again that structure that was a nightmare. You try that. Often people don't like to say they're failures. Don't do that again. Of course, maybe a smarter solution, but that didn't work. So we looked at another way. It's just in the distillation. That's much more in the book. And the following identification problem. So again, we looked at our working horse. This is this one-dimensional array of network connected dynamical systems. There are n of them, and n is very large, in the fifth, sixth, and more. And what we were more interested in, how can we identify a local system somewhere in the middle? Just using local data, whatever locality means, I'm just explaining it. So that was in general the identification problem interest. Okay, so by using only local input-output data, say from a number of neighboring elements, input-output data of the system sigma I, and I define the neighbor here with this capital R, and we look R systems to the left and R systems to the right, where we assume that this neighboring index R is much smaller than the number of systems in the network. And think about this, 10 to the 6, while R is 8 or 10 or so. And that is what we do. And you will see that the fascinating thing that happens when we do that. So that's very important. So can we, by using only this local data, find the system matrices of the system in the middle? Because the complicating factor is, it's influenced not only by input-output data locally, but also by the influence of a neighboring element, which you very see in physical applications when you have a membrane, and you push the membrane somewhere, it influences its neighbors, and you don't know what's happening. That is important in these kind of systems to look at. But it was a challenging problem where we looked into. And this, I will only outline the solution, and I'll show you some simulation results. It was a strategy that we developed, and then you will see immediately what the advantage was. So we looked at, say, identifying the state sequence of R systems to the right. And these are the R systems, this was sigma I here. And that's the system. If you look at R systems to the right, these are the R systems, and they might be 8 or 10 systems to the right. And then we use the local inputs and outputs from these R systems to the right to try to find the state of that lifted system to the right. And that is what I call the lifted system, where we collect all these states into one lumped small dimensional, you know, and just the 10 states to the right. Then there's the lifted system to the right. We try to find the state of that lifted system to the right. And then we see what the advantages of doing that, what is happening here, is that even if you change R, you make it 5 or 6, the unknown inputs disturbing that remain of the same dimension. At least if you assume that all the state dimensions are the same. So the unknown input to this lifted system in dimension becomes always relatively small to the number of outputs that you have. That's very important. We're going to use that example. I hope you understand that. So think about the example that the states of dimension 2. This will always remain a 4, while you can increase this as much as possible by changing R. So if you have only one output for each local system, making R 10, all that it makes is excessive to the number of unknowns. That's very important. As you will see from the definition of the. So that was a kind of striking example, but still we can take R very small, 10 or so is sufficient for to think about in this way. So that's the first thing. And we will show you the conditions when you do that, but assume we can do that. Then we can do the same thing for the systems to the left. And the systems R system to the left of the system I plus 1 also contain sigma I plus 1, because that's the state we want to find. And I will explain in a minute why that is. And so we do the same thing. If we can do this, we do the same thing to the right, to the left. Then this the system which is unknown for identifying our system sigma I, which was the state of the neighboring system to the right, which is xi plus 1, is an intersection of these two states. It's an intersection problem that gives us that unknown state to the right. We can do the same thing for the system to the left. And if we then go back to our equations, what we have done, we have here, and we have peeled out this unknown system to the left. We have peeled out this unknown state to the right. Then this identification problem for identifying these local system matrices and the dimension of the state is just an ordinary subspace identification problem. So that's the interesting thing there. So by this strategy, and the key problem is finding the local states based on this disturbance that have unknown inputs. But as said, the structure of the small lifting there is that these remain constant while we can increase this one, gives rise to a solution which I'll summarize. And so once we have all these quantities, identifying ABC and their sizes becomes a piece of cake. Now, the reason we can do that is the following. So when this lifted system, to the right or the left, lifted, where this dimension remains small with respect to the number of outputs, when that system is strongly observable, what does it mean? I hope you understand the normal observability, and that's the normal observability of these local systems. And the CA pair needs to be observable. But in addition, the compound matrix of the local observability and the tuplets matrix that characterizes the influence from these unknown inputs to the outputs, which is this tuplets matrix. When that compound matrix is full, then you have a globally observed, we have a strongly observable system. Then you can apply standard techniques like monos techniques to find the state by intersection of this matrix. Now, what is important here, and that's where the dimensionality comes into, when this remains the same, when the number of columns remains constant, small, say 4, by increasing R, these become always tall matrices. And hence, the fact that they become full rank, these type of matrices, is kind of enhanced by this choice that we have made. Because this now becomes a tall matrix, and hence the chances of invertibility is much higher. Now, such a matrix and its invertibility has to do with the zeros of the system. And the zeros of the system have everything to do with the sensor placement. So this now, I mean, if you would like to have this condition preserved of strong observability, it can be integrated in the design of the network, because that's where you have to locate your sensors. So this now brings lots of things together, and so the identification problem not only becomes more complicated, but it allows you to also integrate in the overall design of the system. That's what I found very fascinating. And so when this is satisfied, we can solve or work out the strategy. And this is just an example with which I have to close. Sorry, I have enough time because they're not sexy. You just shut me up. But this is an example where all the local systems are the same. And these are the element matrices on the triangular structure. And they are two-dimensional, we don't know that. And then have the B and the C matrices. And now we're going to look for, say, a local system somewhere in the spot. System, I think in the middle. For those who know subspace identification, there is S dimension, the size of the angle matrices. We see we have about a network of 10,000, but we only have to choose R, and the number of neighboring elements about 10 in this perspective. So the very small scale identification problems. And here you see the poles of this local system sigma I in the middle, when we have 2,000 measurements, only 2,000 measurements of local cell systems for identifying the system in the middle. And then when you increase, that is when that is the noise of the output. When you increase, that's the proof consistency of our scheme. Then you see that the poles distribution becomes smaller. Much more can be set about. It's just an introduction. More can be read into this interesting book. It's blue. It's not a Delft color, but it's also blue in there. Of course, there are also applications in there because in my EOC, of course, we focused on development of fundamental methods and giving you some exposure here. But I also had another kind of part in there, which is much more related to the applications of the smart optics. Because what we saw here is that in designing algorithms, you basically have also to change or to modify the hardware. And that's also an important component. I haven't talked about that, but in applications, there's very much on that, how to distribute the calculations, how to operate with the GPUs, etc., etc. It's a very important element also in there.
Sorry, quick question. But related to the structure of the matrix F, no? It is tuplets only because you are assuming now a 1D system,
Absolutely,
right?
absolutely, yeah.
So
We have also generalization for the 2D.
so, but if you have instead of one neighbor to the right and one neighbor to the left, but different degrees, each block has different degrees.
No problem.
So,
No problem. Absolutely.
but then you lose the structure.
No, you see, because of course you lose the structure of the neighboring elements, but we are not interested in that structure, only interested in the state. And in the end, we are interested in a small neighboring states, and that's an intersection problem. So there, the structure is not enough. So that is it. And you can do the same thing with the neighboring elements to the left and to the right. But if you think of 2D, it becomes a kind of a square thing, where you have to work with square. It's a little bit more complicated with the two certain people. It works the same. So if you would like to know more about that, just an introduction and just to whet your appetite, please read this book. And I have acknowledged many people who helped me in the lab and in doing this research. So thank you for your attention.